Hi, I'm Angelina Risi. In this video, I will discuss the history, properties, and applications of the memristor, a relatively new concept even in the field of electronics. First, I'll discuss in brief the background and theory of the device and its development through the present day. Memristors are the theoretical fourth passive circuit element. They were first formally proposed by Leon Chua, a circuit theorist, in his 1971 paper, Memristor, the missing circuit element, but research on such devices had been done for some years prior. In his paper, he theorizes that of the four electrical properties voltage, current, charge, and flux, related by the three known passive electronic elements, the relationship between charge and flux linkages absence indicates a missing element. In this paper, he continues to go into the theory of the device's characteristics, and the problem of being able to model such a device with active components, but not being able at the time to present an actual memristor device following the definition of a passive component. To be considered a passive device, it must have positive power dissipation. This means that IV characteristics must fall into only the first and fourth quadrants during operation. In the case of a memristor, this can be defined as having a purely positive incremental memresistance. However, 37 years later, in 2008, HP Labs published a paper in Nature showing through analysis of a naturally arising memristor in nanoscale electronics. Memristor devices existed before this, but may not have been officially recognized as such. An example they use is a thin-film semiconductor device between two metal contacts, in which part of the thickness is highly doped and the other intrinsic, essentially a thin diode. A common material type is titanium oxide with platinum contacts. The highly doped region has a much lower resistance than the undoped region, and the application of voltage across the device causes dopants to drift, modifying the resistance by changing the boundary of the doped region. Since the doped and undoped regions are in series, we can approximate the memristor as a function of charge from the resistivity of the undoped region and its modified width. Such a device produces the distinctive Lissajous curve IV characteristic of a memristor, and can be considered a perfect memristor under certain operating regimes. In 2015, a startup called Gnome won the race in commercializing memristive memory devices. Their implementation used several metal layers and a chalcogenide layer, with the memristor produced via the conduction of metal ions through the chalcogenide. Their memristive devices are intended for machine learning applications. In the Hodgkin-Huxley model of the neuron, the electronic properties of the synapse includes a memductance, so naturally, the idea of using memristors to mimic natural memory effects for artificial intelligence arose. The anatomy of each memristor device is as so. The electrodes come in chromium, tin, or tungsten. Near one of these electrodes is an easily oxidizable metal layer, either silver or copper. When a positive bias is applied to the electrode near this layer, it oxidizes into ions and forms a channel through the chalcogenide active layers as it reduces. This forms a conductive pathway, lowering the device's resistance, which will dissolve when the potential reverses. This design is known as the self-directed channel memristor. While the current smallest implementation of these SDC memristors is 100 nanometers versus the smallest 8 nanometers for thin film implementations, the fact that it is available commercially and smaller test packages can be ordered gives it an advantage in the current market. Now, I'll explain some of the commonly considered applications when developing these new memristive components. One of the major motivations for developing memristor technology has been to develop compact, stable memory devices. Current electronic memory implementations include dynamic memory and flash memory, which store charge and capacitive elements. While flash memory is relatively stable over long periods of time, dynamic memory must constantly be refreshed due to leakage current. Memristor memory could provide a similar service to that of flash memory by storing non-volatile memory of its resistance for long periods of time, as the last resistance held before power is turned off is maintained. HP is developing the so-called crossbar latch memristor configuration, which could potentially be used as transistor-like elements but with much higher circuit density. This design has been used to generate fast, dense memory arrays, reportedly able to store as many as 100 gigabytes per square centimeter and about 100 times as fast access time as flash memory from a fraction of the energy. In his paper, Chu also proposed the potential to design unique signal processing devices, taking advantage of the special features of the Memristors' IV characteristics. He provides an example of generating an accurate staircase waveform given a symmetric square pulse. Memristors will continue to be used in electronic modeling of both devices and natural phenomena, including electrochemical cells and neural networks. At this point, you might still be confused about how memristors work. Essentially, the idea of memristors is to establish a device with a relationship between flux and charge. We want to develop passive memristors, which only dissipate power, so this relationship must be monotonically increasing, and this carries over into the IV relationship, as flux can be measured as the integral voltage over time and charge of integral current over time. While it is often easier to visualize devices in terms of current and voltage, it is essential to understand the memristor's unique properties make it difficult to characterize on those scales due to the memory properties it possesses. The IV characteristic does, however, highlight the pinch hysteresis effect distinct in memristors. At high frequencies, this effect degenerates, and the memristor converges into a linear resistor. The memristor at its core is a variable resistor, dissipating energy as heat and relaying current and voltage in some way, but unlike common ones as a potentiometer, it is able to be tuned by its electrical input and, if non-volatile, store a value even when powered down. It is also shown to have a different resistance with tuning voltage applied up versus down due to its nonlinear characteristics. Its equivalent memristor property is a function of its charge, though the device is still experimental, so general equations describing memristor may not be well understood. Memristors with significant changes in memristor over a small voltage range may be considered for switching applications, but unlike transistors, their state of charge is not directly related to their applied bias voltage. Memristors are still a topic of debate and research among the engineering community. Soon enough, they may become a well-known and crucial component for circuit applications, and may even be integral in continuing to improve computing performance. For now, while expensive and noble metal materials like platinum, titanium, and silver are being used to implement them, they may remain just out of reach when it comes to full, widespread use and commercialization.